Start recording and share my screen. I'm guessing everyone has their pizza. So thank you so much for coming to all who did to our 14th general body meeting. God, we've had so many of these this semester. If you haven't, I guess you probably have heard me say this speech like 1,000 times now. But please go to acm@uc.org/c, which is for your attendance. It takes like 30 seconds to fill it out and kind of helps us keep track of the attendance. So like how many people we usually have in each meeting. And also something more important is to be eligible to be voting and running for exec, you need to have attended 2 meetings. And one of today's meeting counts as one. So please fill out the attendance at acm@uc.org/c. And we also record these slides. So currently this presentation is being recorded. Just a heads up. Our mission is to encourage professionalism among tech enthusiasts in a collaborative fashion by facilitating learning beyond the scope of classrooms to develop innovative and inclusive ideas. In short, what that means is we kind of want to teach you things that you generally would not learn in classrooms and kind of help you teach or like at least start you off with skills so that you can build up upon it themselves, and also do all of that in a collaborative fashion where you can like learn from each other. What is ACM at UC? Since you're here, you probably know what we are, but if you don't, that's okay. We are the student chapter of Association of Computer Machinery, which is the national, actually probably international organization. But the way I like to describe it is we're a bunch of cool kids or cool CS kids who like programming or technology come together and talk about it. What do? We do events where we have guest speakers and panels at our general body meeting. Like today, our exec member, Daniel, is going to give a presentation. We also do ICPC, we do Revolution UC, which is one of the biggest things that we do. We host socials and review sessions. Membership requirements, you only have to attend 2 meetings, that's it. And for us to record it, you have to sign in, like I said initially, at acm@uc.org/c. And that's it. You don't need to pay any ACM nationals or any fees or anything to be part of our chapter. Code of conduct, please be nice to each other. And I think everyone usually is, and you can find more information at acm@uc.org/conduct to find more information about our code of conduct. Academic services, we do programming review sessions. Like last semester, we did a programming review session for Python programming because they usually teach Intro to Python in fall for CS students, and they also teach it in ENET, so we thought it'd be helpful. And we also have all our past talks on YouTube, so if there's any programming review session that you want to look up, you can definitely check out our YouTube for that. We also do office hours, which are usually Thursday right after this, so when we have meetings, we just hang out over here and talk for a while. We also do ICPC, so information on that will be announced later on. And ACM at UC's community server, this is something new that we've worked over the past year, and the efforts were led by our Vice President Piyush. So we did use it for Minecraft for Revolution UC, and we're preparing it up a little bit so that we can give access to our general body member in some way or the other, hopefully soon. We also have a Slack, probably one of the best ways to get information about all our meetings and everything that we do. So if you go to acmcincy.slack.com/signup, you can sign up to our Slack. It has a mobile and a desktop app, and all our code of conduct applies. Similarly, we also have Discord. You'll get the same information that you get on Slack on Discord. It's a little bit less formal, and we usually do our virtual socials on there. And we also have an Einstein bot, which is sometimes alive, sometimes kind of dying, but still super fun. So definitely scan that QR code if you want to join our Slack. Or our Discord, sorry, I misspoke. Other resources, you can go to acm@uc.org/archive and /resources to kind of know about all our other resources, which are slides and recordings, and you can also check out our YouTube. Now, the big thing, elections. So we're not having elections right now. Our elections will be in the next meeting. So 2 weeks from today will be our elections meeting, but we are starting nominations tonight. So if you are interested in any position, this is the time. We are starting nominations, like I said. So we'll start from president and then go all the way up to webmaster. You don't have to accept or decline right now. So I guess the way this works is if you get nominated, you can nominate yourself or someone else can nominate you for any position. And then you get the option to either accept or decline that nomination. And you don't have to do that right away. You have up until the next meeting for that nomination. You can be nominated for multiple positions. So if you're not sure which position you want to run in, or if you're interested in more than one position, that's completely fine. You can be nominated for more than one. And also, not something super important right now, but still something you can keep in mind is we do trickle down nominations. So let's say you run for like vice president and then you don't get that, you are allowed to trickle down to secretary, even if you're not nominated for that position. So that is something you can keep in mind for the next meeting. But anyone have any questions before we start nominations? I know I spoke real fast and there's like a whole lot of information. All right. So starting off with our nomination for presidency. Anyone want to nominate themselves? Otherwise, I can go nominate some people. Mahesh?
Sure, yeah.
Mahesh, let's go. Bob? Right. Piyush? I'll also write your name down and then do decline. Yeah. Yeah, Piyush/DJ Rapid.
Dave an ACM member?
Is Dave an ACM member? Dave Agarwal? Yeah, he is. I mean, he's attended 2 meetings. So Dave is, yeah. Yeah, if there's someone that who you know would be a good fit but isn't in this meeting, you still can. Daniel? No, I'm nominating you. And Nishil. Those are my 2 nominations as well. Is there anyone who wants to accept or decline your nomination right now? That one I did know. Yo, I like completely is it format? Oh wait, oh it's right here. Sorry, I'm dumb. I remember which color it was. Close. That's the one. I'm pretty sure that's the one. And then what? Is it the other one? What? It's fine. All right. Anyone else wants to accept or decline it right now? All right. If you're unsure right now, that's okay. I'll reach out to you sometime this week or before the meeting, to confirm it. What? Yeah. And this link will also be in Discord and Slack, so you can like accept or decline your nomination via that as well. Nominations, right? Right after the meeting. For vice president, I'm gonna nominate Natalia. Mahesh. Oh. Any other nominations? Oh, Daniel? And then next is secretary. Natalia, let's go. Do you want to be nominated for anything? No. Are you sure?
Yeah.
Okay. Rugved? Did I spell your name right? Okay, sweet. Anyone else? Baru? Oh, I'll also nominate Ayush, who is, yeah, I think he'd be a good fit. And think of anyone else. We could. Yeah. No, we have Slack and Discord. Yeah. Next is, wait, anyone wants to accept or decline the nomination right now? Rugved, I'm assuming you want to accept it right now. Natalia? Just accept it. Just accept it. Yeah. Let's go. Nice. Treasurer. I'm gonna go with Mahesh for treasurer. E. Atharva? Oh yeah. For secretary or treasurer? Treasurer.
Put me on all my adventures, so I'll not
Mm-hmm. Cool. Any other nomination for treasurer? All right. Next, we have webmaster. Oh. Nisha, let's go. Anyone else from web team? Do you think Alan would?
Alan is an active member of BEB, so I'm not sure if he, but I believe it's. He's still a data, I call it thing.
Oh, okay.
Yeah, graduate with Supervised, so I mean, he doesn't know.
Yeah, we can just ask him. Eat. Was there anyone else in web team that I don't recall? We nominate Dave again. Yeah. Anyone out of these who want to accept the nomination right now? All right. We don't technically need nominations for chairs, so we don't have elections for chairs. But if you are interested, you definitely feel free to just show your interest right now. Again, we won't have elections. I think these chairs are appointed positions, and each chair has different responsibility. And it usually is like a great way to start in ACM as well. So if you are interested in being a chair, which is highly recommended, Natalia and Lena, they're both chairs right now. If you have any questions. Oh, also, I was completely not looking at the chat. Oh, Kevin and Sam Shaw. Wait, Liz. Yeah. For what do you want to nominate them for? Kevin for VP. I did ask Kevin if he wanted to. He didn't say anything, but he's still nominated, so I guess we can ask him again. Yeah, but I reached out to him again today, and he said he wasn't interested. And Sam Shaw. Well, actually, you should probably ask last names as well. Sly? Is it SLY? Yeah. All right, cool. Thanks, Liz. Dope. But if that is all, these nominations will be open up until like the next meeting, which is 2 weeks from now. So if anyone changes their mind, or if like you think of anyone else who would be a great fit for exec, or if you yourself wanna run, feel free to reach out to me. We'll like share this in the Slack channel, or like Slack and Discord as well. But without wasting any more time, who's that? Someone lost their phone from the Apple Watch. But without any further ado, we're going to have Daniel come and talk about GAN.
All right. So hi. Let me pull up my slides real quick. All right. So is there anyone who has any idea what a GAN is already? Badri, you don't count. A little bit, Brandon? A little bit, you guys? Cool. So a lot of people don't know what GANs are, but I think they're super cool. So I'm going to do my best to explain them in 45 minutes, or probably less, so that there's time for questions. And feel free to stop me at any point. You can always ask a question. That's the whole point of this. So cool. So GANs. So to kick this off, I want to start with a GAN example. If you're lazy like me, you can just scan that QR code. Otherwise, you can type in thispersondoesnotexist.com on your phone or computer. And when you do that, you will see faces like the ones you see at the bottom there. Those are just some examples of ones that are generated on that website. I'll give you all a second to do that if anybody wants to. So this is one of my first experiences with GANs, my first time even encountering the output of one. And I find this one to be very impressive. So all the people that you see on that website, when you refresh the page, you'll get a different face. But those people are not real people, hence the name, this person does not exist. They are generated from a generative adversarial network, which is a GAN. And basically means that it trains on a very large data set of pictures of human faces, which we have plenty of, so it was probably a very, very large data set. And it was trained very, very well. GANs are difficult to train, so this one in particular was trained very well. Do note, though, that it's still possible that the GAN had really weird output on occasion. It's possible that people came with, jacked up eyes or, a third, ear or something. Very possible that this GAN is not perfect. But what they do on the website is it almost deceives you into thinking that you're viewing live output from the GAN. But really, it's the developers of the GAN picking and choosing output that looked really nice. They're like, oh, so the GAN did still generate all of these faces, which is still very impressive. But do note that it's unlikely that you're going to find an image that looks distorted or not perfectly normal like a person. Although it is, I've seen it happen, but it's very rare. So what are GANs exactly? So firstly, I can describe them as unsupervised generative deep learning models. I'm not going to go super in depth on what deep learning is and what neural networks are because those are kind of more broad topics. But the keywords here are unsupervised and generative, and I'll discuss both those in detail on the next few slides. And it's composed of a generator model and a discriminator model. These are both neural networks, so there's two of them in a GAN. It's not just one. There are two neural networks engaged in a minimax, otherwise known as a zero-sum game, and I'll also describe that keyword later as well. And they output synthetic instances of data that can pass for real data. So as you already saw, and this person does not exist, those are synthetic instances of human faces that pass for real human faces. So you can see a lot of applicability with GANs already just from that. So getting into it, we'll first start by looking at supervised versus unsupervised models. So supervised models, the main distinction between them and unsupervised is that supervised models use labeled data sets, which is honestly what you'll see most of online. When you're looking up data sets, which, by the way, I had to do a lot of this for my senior design project because we were looking for data sets to train a GAN on, which is why I'm doing this presentation now, because I've spent the past 2 semesters researching GANs and making one myself. So me and my partner had to find lots of data sets that were available online, publicly available. Of course, we could have created our own, but to train a GAN, you need thousands and thousands of images. So a lot of the data sets that we saw online were labeled, meaning that they'd come with a folder full of dogs. And each one of these photos is accompanied by a label saying this is a dog, because computers don't know otherwise. And same with cats and foxes or whatever it may be. They're labeled data. So it's not just an image that we can obviously interpret, but it's an image paired with some kind of key. And supervised models train their algorithms to classify the data, which is pretty much what you see almost all of the time, right? You'll get these hackathon projects and things that you show it some image of something, whether it be a human face or your right hand or left hand or whatever, and it'll say that's a hand, that's your face, that's a cat, that's a dog, because it's trained on these, knowing this is what cats look like. These are cats because you're telling me that they're cats, or these are dogs because you're literally telling me that these are dogs. Once it does enough training, then you show it an additional dog, and it's like, hey, that has features that look like features I already know about. Those are dog features, so I think that's a dog. That's what supervised models do. And they're very accurate. They can be if they're trained long enough. But they're bad for really big data sets. If you have a lot of data, they kind of lose their efficacy. It's harder to train the model. So that's kind of the disadvantage there. Some examples of supervised models, or problems that supervised models solve is obviously classification, as I already said, and regression, which is kind of like interpolating data based on existing data. So if you had like a company and they had some sales data over the years, it can predict what the sales data is going to be in the coming years. Unsupervised models like GANs use unlabeled data sets. So it's just, instead of having these dogs accompanied with, hey, this is a dog, you're just giving it the picture. You're just saying, here's a picture, figure out what it is. And so at first you're like, well, how does it do that if we don't tell it? I'll get to that later on how a GAN actually works in that regard. But you can also give it several different types of data in the same data set. You can give pictures of dogs and pictures of cats and pictures of foxes, and it has to figure out how do I separate these? How do I distinguish between what's what, since you're not giving me labels? So again, unsupervised models find these hidden patterns within the data without requiring any kind of human intervention at all. Whereas supervised models, we have to go in and say, we have to classify all the images ourselves first, say, because we know that's a dog, we know that's a cat. And I'm going to keep saying cat and dog throughout this whole thing, so bear with me, just to keep things simple, but it could be anything in theory. And unsupervised models are good at handling big data, but they're also very hard to train, and so they risk having some inaccuracy with them. So in that regard, there is a little bit of human intervention that needs to happen. You do need to be paying attention to the output and qualitatively look at it and say, hey, this looks like what I'm expecting you to create, or what I'm expecting, you know, like you have to check those data sets and see, oh, you've clustered all these images into what you think is one set and all these into another set. You know, you think these ones look like cats, you think these ones look like dogs. Not that it knows what cats and dogs are, but it knows that they're two separate things. That's kind of the gist of it. So you do have to look at those and be like, make sure there's no coyotes in the cat set, you know, make sure there's no wolves in the dog set. So it's not going to be perfect. You're not going to get perfect accuracy generally. So examples of problems that unsupervised models can solve is clustering, which is kind of how I just described it. So when you have many different types of data fed into the neural network at the same time, it can cluster that data into similar feature sets. So to say all these images have these similar features, so I'm going to cluster them together. I'm going to cluster these ones together, and just they figure out all the different sets, even though you didn't tell it anything. You could have given it dogs, coyotes, and cats, and it'll figure out that you gave it 3 different things if it does it properly, if it trains properly. Also, unsupervised models are good for association problems. So if you feed it a bunch of, for instance, like shopping data, you know, of data people shopping at Target or something, it can figure out, it can say, you know, if people buy diapers, then they're likely to buy baby wipes and baby powder as well, because it figures out how these things are associated with each other. It sees those associations in the data, even though you didn't tell them that they were associated. It just figured it out because that's a pattern, right? And that's how you get your recommendations on Amazon or your ads and things like that. It figures out the associations between the things that you've been searching or buying and can recommend things accordingly. And it can also work in dimensionality reduction problems. So lots of input, especially real life input, such as audio input, video input, and even images, have a lot of extra noise that the network doesn't necessarily care about. And that adds dimension to whatever the input type is. So dimensionality reduction is where it will take those inputs, pass them through the algorithm, and essentially eliminate all the extra noise, the things that don't pertain to your data. So in real life, we do this very easily when someone's talking in like a crowded room. There's all this noise, and anyone who's like hypersensitive to audio can attest to this, that there's a lot more than just the person you're talking to going on. Our brains are good generally at filtering out all the extra noise themselves, but computers don't do this as easily. So with audio, especially in like music production with vocals, you want to filter out all that background noise. Even if it's very minuscule, you want to filter it out. So it'll reduce the dimension of the audio input data that it's receiving and maintain the integrity of the data that you actually want. You still want to hear every word and pronunciation that the singer is saying, or the person talking to you in a crowded room is saying, without all that extra stuff. So that's dimensionality reduction, and that does come into play with what GANs can do as well. But I'll get to that later in the PowerPoint. Are there any questions so far? I don't want to spew so much stuff. Yeah. Well, I'm not sure exactly how YouTube does it. They might not even use unsupervised. Like I'm not sure, because you can use supervised models to do some of the things that unsupervised can. They're not really built for it. You know, it might be more difficult, but maybe YouTube's going for accuracy or something, so they're using a supervised model, and vice versa. There are unsupervised networks that can do things that supervised networks can, but they're just not as good at it by nature. Yeah, so I'm really not sure. I can't answer specifically, but it's possible, and that'd be kind of interesting to know that YouTube has no idea what is actually going on with your recommendations. It's just getting all that data, and it does it itself.
Well, you can actually see like at the top of the browser, they have like a list of all the kind of topics that you're into.
Oh, yeah, yeah.
And so they cluster it, but then they must have some kind of labeling that they know that,
oh, yeah.
Oh, you're into skateboarding.
Well, even the specific channels and stuff, it'll know like who you tend to watch and stuff, and so it'll pull up, but there's a lot of stuff behind the scenes. What is it?
Isn't there an algorithm for recommender systems?
Yeah, there's a whole.
Yeah, probably. Yeah, there's a whole bunch of specific algorithms, and these aren't specific. These are just the general categories of those algorithms and the types of problems that they can solve. So I've described the unsupervised part, but now I'm going to describe the generative in generative adversarial networks. And this kind of goes into a whole nother thing, which I'll get to in the next slide, but discriminative models, and I know I'm going to screw up that word one time or another, so, you know, discriminative models classify data. Sound familiar? They predict the categories associated with the input. That's like a supervised model, right? They classify. It can't group things itself, it just classifies. It says, you know, you give it an image of a dog and it's going to say, that's probably a dog if it was trained right. You know, you give it an image of a cat, it's going to say that's a cat based on the features you trained it on. So it maps those features to the labels that were already established because it knows what the labels are. So when you give it something that has similar features to a cat, it's going to assign it cat. It's going to map those features to that label. And it learns the boundary between the classes. Again, if you can imagine having several data points on a plot, some of which are cats and some of which are dogs, it's going to know where to draw that line and say, you know, if it's on one side of the line, it's a cat. If it's on the other side, it's a dog. It finds the boundary between the classes. Generative models create data, hence the name generative, and they predict the features about a category of input. So you give it a bunch of different types of input, it's going to predict what features are associated with whatever category it's starting to form as it trains. And so it maps the labels to the features rather than the features to the labels. So you give it all these features and it's like, well, I see all these features that you've given me, I'm going to put them in one group, cluster them, and label them, you know, group A. It's not going to just be like, oh, those are dogs. It doesn't know that they're dogs, but it's going to assume that it's a particular group. And so they learn the distribution of the classes, not just the boundary between the classes. And I really like this image here that shows you how the difference between discriminative and generative as far as like what they do. Any questions on that? Discriminative versus generative neural networks. Cool. So getting into GANs. GANs have a generator and a discriminator, like I said earlier. They have both. And I really like this quote that I got from a scholarly article. And it says that we can think of the generator as like a counterfeiter trying to make fake money. And the discriminator as being like police, which are trying to allow legitimate money and catch the counterfeit money. So this kind of becomes a game and as far as neural networks go. So to succeed in the game, the counterfeiter needs to learn how to make money that's indistinguishable from genuine money. And then the generator network, or the police, have to get better at creating samples that are drawn from the same distribution as the training data. So that last sentence is kind of a mouthful because it doesn't really follow the analogy. But I really like it, and that's why I underlined it. Drawn from the same distribution as the training data. I'll linger on this analogy for a moment just to make sure that it's crystal clear. But you know, if you have a counterfeiter and you have the police, as far as a GAN goes, the police, the discriminator, is being trained on what real money looks like. You're giving it a bunch of images of real dollar bills and you're saying these are what real dollar bills look like. Then the generator or the counterfeiter is they know nothing about what real money looks like. to start in a GAN. This kind of diverges from the real life analogy. But in a GAN, the counterfeiter is going to start by just guessing. It's just going to, it might have just a blank piece of paper, and it'll give it to the police and say, here, this is genuine cold hard cash. And the police is instantly going to be like, no, like it's not actually. And so it's going to that feedback goes back to the generator, the counterfeiters. And they're going to try again. They're going to say, oh, well, they don't think it's real money because, all the money that they see is green or whatever. So they're going to color it a particular color, whether it be red or blue, give it back. And this is going to repeat over and over. And the police are going to keep saying, no, that's not real money. No, that's not real money. Eventually, they'll get to the point where maybe it's green and it has a face on it and some numbers. Then you're getting somewhere. Then all of a sudden, this generator, this counterfeiter is actually getting decent at generating what looks like real money, but it's not. Like you as a human can still tell it's not real money. So this generator and discriminator are going to go back and forth in this pattern until eventually ideally, if you do all the training right, the generator will be creating money that really does look like real money. And even as a human being, you might look at what the generator spits out and say, I don't know if this is a generated image of money or if this is actually a picture of a dollar bill, which is the magic behind GANs and goes back to that this person does not exist. So yeah, we'll describe that a little bit more. So the generator's job, talking in terms of an actual GAN now, is used to create new plausible examples from whatever input domain you give it. So if you give it a bunch of dogs, then its job is to generate pictures of dogs that look real. And it's trained to minimize the probability that the discriminator is correct, or if you want to see it in a different light, maximize the probability of the discriminator being incorrect. So the generator, again, think of it as our plagiarizer or our counterfeiter trying to make money. Its goal is to make it so that the police are always wrong. Like they'll be like, I think that's fake money, and they'll be like, actually, no, that's real money. Versus, you give it something fake, and the police are like, well, I can tell that's fake. They don't want them to guess it properly. And you can view it either way, vice versa. And the discriminator, its job, again, as I said earlier, with all discriminative models, their job is to classify examples as real or fake. So this is like, it kind of goes back to like the whole police investigating the counterfeiters, right? So they're supposed to tell you whether or not they think something's real or fake. So they're trained to maximize correctly categorized images. Maximize the number of images that they correctly categorize, right? They want to obviously be right when they see a fake dollar bill, they want to say, hey, that's fake, versus they get a real dollar bill and they're like, yep, that's real, because they don't want to be throwing people in prison for money that is actually real. So I saw some of y'all getting weak, and I see why now. So once the training is done, the discriminator can be yeeted, as I like to say, which I actually think is really cool. And I think that's why the name Generative Adversarial Network sticks, because like I said earlier, a GAN is composed of both a generator and a discriminator, both equally. They're both equally valuable until it's finished training. Once it's done training, you only need the generator, because the generator has been trained to make this data, and then you can just throw away the discriminator. You don't need it anymore. And that generator remembers all of the weights and things it has with the probability distribution to generate images that you fed it. So the generator alone, once training is over, will give you those realistic human faces, or those realistic dogs, or realistic cats, whatever it may be. So the discriminator is only there temporarily to help the generator get better at what it does. And the discriminator in turn also gets better at what it does. Does that make sense? I know that's it can be a lot to process at first. Are there any questions about the generator or discriminator?
Make it until you make it, and eat it until you created the world's greatest counterfeit criminal.
Well, it's don't yeet. Don't yeet until you don't need to yeet it. Yeah, right, because think about it. If Josh is an undercover cop and I'm this counterfeiter, Josh knows everything the police know. He's got access to the database, all that. If I keep working with him, he's working with me to plagiarize money. He's going to use all the techniques that the police are going to use to tell me whether the money is fake or not. So if I keep working with Josh for a long enough time, I'll have a really realistic dollar bill that Josh won't even be able to, be able to do nothing but guess. So an ideal GAN, when you give it a generated or real image, the discriminator or the police will be able to do nothing more than just guess. It will be able to say, well, I don't know, so it's real. It just guesses. So 50% accuracy is the best you're going to get with a discriminator in a GAN. So once you're at that point, that ideal point, then you can throw away the discriminator. I don't need Josh anymore. I got my real money. I know how to make it. So you only need the generator. You only need the counterfeiter. Or in this case, yeah, well, the generator. Yep.
Just maybe like nitpicky and honestly not just because of the example, but at the end, do we want the accuracy to be 50% or is it like a higher?
So you're.
Because then the discriminator could be like, oh, this looks like a real counterfeit. So like, oh, I think it's true.
So I think you're mixing up between the generator and the discriminator. So with like this person does not exist. If I give you an image from that website, I tell you this is from this person does not exist, and you look at it. Or well, I'm not going to tell you it's from this person does not exist, I guess, but it is. Let's just say that. And I give it to you and I say, is this a real or fake person? You're going to be like, hecky sus, right? Because I just asked you if this is real or fake. You're going to be like, why would it be fake? Because it looks real. At that point, you're pretty much going to guess. As a human, you're going to be like, I don't know. It could be fake. It could be real. I don't know. You just gave me this image. It looks real. Once we're at that point, because you're guessing, your accuracy is going to be 50-50. You're just flipping a coin. So that's when you know your generator, whatever image I gave you, whatever's making that image is perfection, essentially. Because you can't guess anymore. You can't do any better than just guessing, So does that kind of make sense? Because I know 50% accuracy doesn't sound good. You want it to be like 100% accuracy, right? But you can't be 100% accurate because that discriminator is going to be like, well, it doesn't know anymore. Like,
well, that's kind of the goal too. Like the goal is to have the generator work so well that it like breaks.
Right. Essentially, yeah. If you want to think of it that way.
That makes sense. Asking the question like, is it real or not? Because I was thinking, oh, this is like 80% close.
Yeah, 100% like looking like what it's supposed to. Yeah, no. So this is the accuracy of the guesses, the accuracy of whether you think it's real or not. I saw your hand up first.
So would there be a case where you'd be training a GAN and it actually in hopes of improving a discriminator versus improving the generator? So instead of just throwing away the discriminator at the end, you're basically training to train the discriminator instead of training to train the generator. Would that be a case?
It could be a case. I mean, because again, this goes back to what I said about discriminator models. Discriminative models can be used to classify data. That's the point of them. So what you could do is train this discriminator so that it's very good, like it's nearly perfect at picking whether or not, like, oh, I think that's counterfeit versus, oh, I think that's real, for cats and dogs. And then you give it a picture of a dog. Let's say it's trained on cats. If you give it a picture of a dog, it's going to say, no, I don't think that's a dog. So it solves the problems that I mentioned earlier with discriminative models. So it can do that classification. So yeah, you don't, like, I say throw it away, but as far as a GAN is concerned, like the purpose of a generative adversarial network, the reason generative is kept in the title is so that you can keep the generator and use it to generate new things. Does that make sense? Cool. Natalia, you had your hand up.
So can it only be done with images or can it be through the images have to be 2D, can it be like 3D?
Oh, it can be like anything. I'll get to that later. Yeah, I'll get to that later. You'll see it. It'll be super cool. That's the fun part. This is the boring part of the lecture, by the way. So I called it a lecture. That's how you know it's boring. So this is kind of just a basic model of a GAN, and I like this picture. It's not perfect. I just found it online. I'm too lazy to make my own. But essentially, and I circled the word latent space because I'll describe what that means a little later. But basically, starting out, the GAN, the generator is just, like I said earlier, the counterfeiter, it's just going to hand something random. We're giving it some random noise, and that's going to go to the discriminator. The discriminator has already been receiving these real samples of money or whatever it may be. Let's just say real dogs. And the generator's like, here's a dog, and it looks like static black and white, like it doesn't look anything like a dog. the discriminator is going to do a pretty good job of being like, nope, that's not a dog. Then based on, so the discriminator is correct. So on the right, you can see that D, the discriminator, is correct. That's going to go back to the generator and tell the generator, you're not doing a very good job at making dogs. So the generator is going to adjust its weights and adjust the weights of the functions that model a distribution for the images. I know that part's really confusing, and I'll kind of get into that a little more later. But just take my word for it. The generator is going to learn from that output and generate something that looks a little closer to a dog the next time. Just a little bit closer. So because training a GAN takes a long time, hours and hours, especially if you're using your own computer or not using a GPU. It's going to take days to generate a GAN to a point where it even looks relatively like what you want it to. But basically, this feedback loop is important to both the generator and the discriminator. So if the discriminator finds out that it was wrong the whole time, it finds out that the generator actually tricked it somehow. The feedback, knowing that it was wrong, is going to also go back into the discriminator. You can see that up there. It goes back up into the discriminator as well. And so it'll do better next time at differentiating between whether or not something's real or fake. So the success of one is basically going to bite it in the butt. So if the generator does well, the discriminator is going to learn from that. Whereas if the discriminator does well, the generator is going to learn from that. And so they feed off each other in a zero-sum game. That's why they call it a zero-sum game, because if one gains, the other one loses, and it kind of cancels itself out. And I think, what was the other term I used? Minimax, right. And I kind of described that earlier. One of them is trying to maximize its success, whereas the other one is trying to minimize the success of the other one. So it's like a minimax game in that way. Any questions on the way that a GAN looks like from this model?
Is data space just a collection of data you're getting?
Pretty much. Those are the next few slides, so you'll see that. But yep. So it's an adversarial model. I'm gonna get to that. So we got two adversaries here, right? So GANs are adversarial in that they're very sensitive to changing parameters, and a lot of experimentation goes into making sure the generator or discriminator doesn't overpower the other. So if one of them gets too good, the other one basically won't be able to keep up. And that can result in a lot of issues with your GAN. I won't go into detail on that. Like it can get to the point where let's say the generator is constantly fooling the discriminator, and the discriminator is not learning from its mistakes in this manner. Then the generator is going to keep making this thing that doesn't look like what you want it to. Let's just say it makes a purple dollar bill. It looks exactly like a dollar bill, except it's purple. And so we all know that's not a real dollar bill because it's purple. But for some reason, the discriminator can't wrap its head around that. It doesn't understand that it's purple, therefore it's not real money. That feature is not one that it's been trained well enough in regard to. So in that case, what you're going to get is a bunch of purple dollar bills because the generator knows that it always fools the discriminator when it makes a purple dollar bill. So you have to be really careful in that sense. And that's why it's adversarial. And I think you can kind of already figure that out because they're kind of adversaries with each other. These two neural networks are competing against each other. And sometimes to resolve this, you'll have an unequal proportion as far as your training epochs between your generator and your discriminator. So let's just say the discriminator is having a tough time with the purple green dollar bill thing. So you only let the generator train on one epoch. You only let it get that feedback once. So it gets a little better. But then you give the discriminator 5 times to try to learn. And sometimes if you modify that proportion or modify the learning rates, if you're familiar with machine learning at all, the learning rates can come into play there as well. But changing the number of epochs that each neural network gets to train on can affect the output of your GAN. So yeah, that's pretty much that. So then we're going to get into image convolutions. I've described everything about discriminative versus generative, supervised versus unsupervised, and the meaning of the word adversarial, as well as discriminator and generator. Now that we know all those terms, we can get into like the nitty gritty of like what a GAN actually like works with. And I'm only going to briefly discuss it. And so Piyush kind of mentioned it earlier with the latent space. And that's actually in detail in the next slide. But I'll keep this part really simple. This is another model that I found online, but I do kind of like it. So you get this it says this input random variable. This is like the noise that you're going to feed a generator. You just give it some random noise, something that doesn't mean anything. It'll just be like static. Like once it's formed into an image, it'll look like static. If it's RGB, it'll be in color, or it might just be like black and white. It'll be just like pixels, and you'll see nothing but static. But as the generator learns, it's going to learn to modify those pixels. And so in this case, you're just seeing one dimension, so it's very easy to visualize. But the generator is going to do some linear algebra, essentially, on that vector and model it in such a way that once it goes through some convolutions or changes, it'll come out looking like, maybe that's a dog or something. I don't know. But it's kept really simple so that you can see once it changes that vector and then goes through a few different convolutions of that vector to change its, turn it into a matrix, essentially, a matrix of pixels, you'll see something similar to the input data. And so it's doing that all through distributions. It's getting distributions from your input data. And then the generator is able to model that distribution and generate things that look like it. So the latent space, this kind of goes into detail on the generator, because the generator is a little bit more complex than the discriminator as far as like code goes. So the generator is actually composed of an encoder and a decoder. And so to put it really simply, it takes whatever image you give it, it encodes it, turns it into that latent space representation. It's going to go through several layers of like different activation functions, and it'll have like some dropout, so it'll get rid of certain things. But the main thing it does is convert that 2D representation of a picture or whatever input you gave it and turn it into something that it can work with really easily and computationally fast. That's the latent space. So the latent space doesn't really mean anything to us, but it does mean something to the generator. It can work with that. Latent actually means hidden, so it's like a hidden space representation. The patterns are visible there that we can't really see. In the images, we can clearly see patterns. We can say, well, every cat has 2 ears, every dog has 2 ears, dogs have a snout, and cats have whiskers or whatever. We can see those things qualitatively, whereas the generator can't really do that. So it needs to convert it into a format, usually just a vector, or something that's not super crazy as far as like dimensions. So something with lower dimensions, so that I can work with it quickly. The computations are faster. Once it does what it needs to do, once it takes what it's learned from the discriminator and changes that latent space into something that it deems eligible to be whatever it is you're trying to generate, then it'll reconstruct that image kind of with like a mirror image of what you did the first time, right? Because you took that image, converted it into this latent space, and then all you got to do is the opposite of that, essentially. You just do the same convolutions in reverse. So you size it back up to whatever your original resolution was. Does that make sense? I feel like that was kind of a complicated thing code-wise for me as I was making my GAN this year. But it makes sense to me now, especially after making this. So yeah. So that brings me to the last part of GANs as far as their output. So how do we know that a GAN is doing well? Well, as I said earlier, you can easily tell how well a GAN is doing just by looking at what it's generating, right? You can see qualitatively whether it's generating what you expected it to or what you're training it on. But sometimes you need something more involved than that. So we have loss functions. And loss functions in general are used to derive the gradients, which are used to update the weights of neural networks. Notice I said neural networks. This is very general. This is just broad. So any loss function in any neural network is trying to derive gradients that are used to update its weights. And so when I say weights, I mean it's some long polynomial that's supposed to model some distribution of data that it's receiving. So in the case of GANs, it's trying to model the distribution of the real data that you've been giving it with these functions. And so in the case of a GAN, we want to balance the loss between the generator and the discriminator. The loss on one or the other shouldn't necessarily be 0 because that's not what we're looking for. We're looking for this equilibrium. We're looking for the GAN is the generator is helping the discriminator, and the discriminator is helping the generator. So as long as the losses are fighting each other, as long as they're maintaining some kind of equilibrium and converging in a graph, then we know we're doing a good job. And so the loss functions reflect the distance between the distribution of the generated data versus the real data. And so this image kind of makes that clear. Again, the captions are kind of just pulled, are all from the internet, but the image itself is what I was looking for. So that higher, or the more normal looking curve there, the one that's just like a basic bell curve, we're going to pretend that that's the data distribution of the real data. Whereas the GAN is trying to model that distribution as best it can. At first, it might just make something crazy that looks nothing like that line, which is where you get that garbage data. But then you get something, as the more you train, the closer it'll model that curve. And you can see that it says a generative network can be targeted to learn selected low probability features through additional training. So you can see how right there at that like local maximum, it's trying to get closer to the curve in that space. So that could just be like a particular feature that you really want to see. Like, you know, like, okay, it's screwing up the dog's ears and it's screwing up the way the fur looks a little bit, but you really just want the eyes to look good. So in that case, you could train on like a particular feature more, and it would closer match the distribution. Yeah, and then the last little bit I'm going to go into on loss functions is that there are several different types of GANs. People have been experimenting with GANs for the past 7 years. I think it was 2014 or 2015 that the first major research paper on GANs was done. So there's several different kinds of GANs. They all have different loss functions that are all attempting to tackle different problems or improve upon GANs. I have at the bottom here that loss functions depend on what problem you want to solve. So picking your loss function is important. But overall, I think there's like a particular score. I think it's called an FIC or something. I don't remember what it stands for exactly. But there's a way of assessing the success of a GAN that's used pretty universally, and scholars tend to agree on it. And they found through a lot of testing with all of these different types of GANs that score tends to be relatively the same across all the different loss functions when you keep everything else constant, if you're like working on the same problem. But for individual problems, using different loss functions can yield a better output. So again, a lot of complex math. I won't go into detail. Badri could probably explain it to you, but I can't. So I won't go into supreme detail, but I will. That's what I'm hoping to research more next semester. So these are some examples of loss functions. The one on the left is not a good loss function exactly. You can still see there's learning occurring, especially in like the first 100 epochs or so. But then those two loss functions don't converge. They don't come together, which means that at a certain point it stops learning and it needs to still be learning because they're not converging. That was actually the loss functions from the GAN that I made for my senior design project. So I didn't quite get to the point where I could refine my GAN because it takes a lot of time and computational power. I do want to do that moving forward. But as far as what I actually turned in for my senior design project, not a perfect GAN because the two losses from the discriminator and generator aren't converging. But on the right, you can see this is just some random one I found online. But that's what an ideal loss function convergence is going to look like. You have that equilibrium. Sometimes it'll be like they'll go back and forth. You know, eventually the generator will get the better of the discriminator, but then the discriminator will come back. That's when you really have something good going on with your GAN. I know I have 5 minutes, so I'll try to make the rest of this a little bit quick. But I'm at the fun part now, like quote unquote fun part, because we've gotten through basically what a GAN is and how they work. This is an example of the MNIST data set. MNIST, if you're not already aware, is basically a huge database of like written out numbers. So on the right, you can see just a bunch of 2s that are written in a different way. MNIST is trained on all of the like 0 through 9. And then after a certain number of epochs, you can see in this GIF, it gets better and better at generating an array of different numbers. You can see it kind of favors 1 a little bit. Ideally, it should be like an equal representation of everything. But other than that, this GAN looks pretty good. It does a pretty good job, even after only 50 epochs of generating what look like handwritten numbers. And every time you run the GAN, it'll generate something different. So it won't just be the same every time, or it shouldn't. If it comes out the same, then that's a problem with your GAN. So I made a GAN that generates pictures of cat faces. That was fun. Sorry, I'm a cat person. So epoch 24, looking good, right? Some pretty kitties up there. Epoch 96, hey, maybe there's some ears and stuff, I don't know. Epoch 222, they starting to look like cats, right? That's as good as I got, so don't be expecting anything more. That's what the input data kind of looks like. That's an example of what the input data looks like. So not too far on, I didn't do too bad, but there's definitely some issues. I think there might be some issues with the image convolutions. You can see there's kind of like a crisscross pattern on some of my cats. Some of them look very similar to other cats. That's another problem with GANs called mode collapse that I need to deal with. But again, GANs are very hard to train. If I've learned anything from my research on GANs, it's that they are very hard to train and they're very hard to adjust weight, every single parameter just right so that you get good output.
Is there a way to give your data like a perfect data set?
Not really. I mean, good data sets are generally diverse. You know, you want to have all different kinds of cats and backgrounds and everything. So that way it'll generate you diverse output because you don't want it to constantly be giving you the same thing. But yeah, diverse is better. Other than that, I mean, bigger and more diverse is better for a GAN. Any other questions?
Can you please explain, can you give an example when the discriminator overpowers the generator, and can you explain why that's a problem?
So if the discriminator, so I haven't thought of this precisely, but if I think about it logically now, if the discriminator is constantly getting the better of the generator, that would mean that the generator is not learning, and therefore the discriminator, let's see, if the generator is not learning, somebody wants to help me, you can. Huh?
Or it's not learning fast enough.
Right, or if it's not learning fast enough, then essentially the discriminator will always be able to tell what the generator is trying to make, and so it's just not being helped. Like at a certain point, it doesn't know what's wrong with what it's generating, if that makes sense. So it can't figure out, it's going to keep trying to make, it's going to change things kind of verbatim. It's just going to be like, okay, well, take this. And the more that the discriminator says no, 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 the more lost the generator is going to become.
Can it be that the discriminator's feedback is not, the feedback is not good?
That's possible. That could be possible too. I mean, especially if the discriminator is not being trained, like if your convolutions are wrong for your input data, that's probably how that issue would occur. So if your input data going into the discriminator isn't being turned into something that it can work with easily, then it's possible that it's like, it's essentially trying to discriminate against the wrong thing. So it's thinking that the generator is trying to make one thing when really it's trying to make whatever it is you actually want it to make. So it's going to be saying no when really the discriminator should be saying yes, or vice versa. Essentially giving, like what Piyush said, giving the wrong input to the discriminator. So if the generator, to the generator, if the discriminator is giving invalid input, then the generator is just going to get really lost.
So it's like it is like justified to say that like the better the discriminator, better the generator, they shouldn't be.
Right. You don't want one to improve so much better than the other, because then the other one will get lost. And you don't want one trained the wrong way in the first place. So it would almost be like, going back to the example earlier, if Josh is the police department and he thinks that some dollar bills are purple when they're not, then I'll be giving him green dollar bills and he'll be like, nah, nope, it's not purple. I think they're supposed to be purple. Then I'm going to be like, what? And so my output's going to get worse. I'm going to start making purple money, and that's not really the case. So that would be an example of Josh getting the discriminator getting invalid input.
Were you almost going to say that?
Huh?
Were you almost going to say that?
No, I don't know what I was doing. I was just stumbling my words. So these are the last few slides I have. I know it's 8 o'clock. If anyone needs to leave, you can, but I have a few slides very briefly, just some applications of GANs. So obviously we've already this is the most boring. I'm going in order from boring to least boring. So this is the least boring right here. So this is just generating synthetic examples of image data sets. That's what I've basically been talking about this whole time. And those could be used in like advertising or marketing. You don't have to hire someone and take their picture, them smiling with your toothpaste or whatever. You can just generate one, and there you go. You don't have to pay anybody to get a picture taken. They're imposters, right? So this one I thought was kind of cool. You can do emojis to realistic pictures and vice versa. So you can give it a picture of a person and it'll kind of generate something that looks like a Bitmoji or whatever you want to call it. Some of them are a little jacked up, so you know it's not trained perfectly, but I thought that was kind of neat. Poor dude that looks like the sun and the vampire guy. Right. Then we have some text to image translation. I think you were kind of talking about this. I think it could, in theory, generate text itself. That's, I think, what you were talking about. It could do that. But generally, GANs are better for images because they're complex input, whereas text really isn't that complex. So in this case, you give the GAN a sentence, and based on its training in like the categories that it's determined, it'll generate pictures of what it thinks you typed. So there's some just examples of that. Clothing translation, I wish I had this for all the steal his looks that I make. Because then it basically, if you have a picture of a model wearing a particular article of clothing, it can extract that clothing item and say, this is the item. This is what they're actually displaying. So you can see all those red coats or whatever are examples of what the GAN thinks that that model is wearing. Same with the shirts and things below. Photo and painting, there's only one more after this. So this is pretty cool in my opinion. So if you just have like a photo and there's just like a part of it like ripped away, let's say it's some old picture or something and you want to restore it, a GAN can, based on its training, restore the part of that photo that was missing. So where it says R's over there on the right, that's just the output of whatever GAN was doing that. So you can see the real versus the R's with all of that data missing. And that's like main data. That's like the way the eyes look and the nose. Like that's pretty important with a human face. And I'd say it does a pretty decent job of generating something that at least looks real. Maybe it doesn't look quite like the actual image, but it does do a good job of generating what looks like a real person there. So I'd take that. I think that's pretty neat. So yeah, that works with any of those other images you can see there. And so I thought this was sweet. I was like, GAN's gotta be able to work with videos, right? So GANs can actually train on videos, really short videos right now. They're not at the point where you can have it generate a whole movie for you. But they at least generate what looks like, I'd say they're at the point where they generate realistic, in a sense, movement. So especially with like the trains and the waves, those are pretty deterministic movements, like you know what's going to happen. Waves always kind of crash the same way. So it does a pretty good job at modeling what waves look like. All of these videos are coming from an image alone. Like it is solely being given an image. So you give it an image of the ocean and it will convert that image into what it predicts will happen, which I thought was really cool. It essentially predicts the future or what the most likely future is based on its training. So speaking of training, you have the trains up there. Obviously all trains just move. So that's kind of what it's trying to replicate, the way that a train moves. And also, I've really blown these up too. They were only like 28 by 28, or not 28 by 28, but maybe 128 by 128 pixels. And I blew them up a lot, so they don't look quite as good when they're all big like this. And the ones on the right, I think are like soccer players. And I think there was some golf training too. So, you know, if you gave it a picture of Tiger Woods, like, you know, it would probably generate a short video of just a little swing, because that's what it predicts is going to happen. Yeah, but you know, the people aren't like floating up into the sky, right? Like it's doing a decent job at modeling what the motion would look like, even though they don't really look like people. Any questions? That's all I got.
When you say that they're unsupervised, isn't that really the discriminator is looking at the region itself?
Yes, I'm so glad you mentioned that, because that's actually a point that I kind of meant to make. So the magic behind a GAN is that although it's an unsupervised problem, any generative network is generally unsupervised. The fact that we're also utilizing a discriminator during the training process is kind of like it is framed in such a way as a supervised problem. So the discriminator is supervising the generator. But I guess the reason that we still consider GANs to be unsupervised is because I don't have to do anything. I just have one discriminative network and one generative network, and it kind of supervises itself in that way. Because the whole detriment with a supervised network is that you have to go in and classify all of the images yourself, which is time-consuming and annoying. But yeah.
Is it true for just one category it's working, then you can say it's unsupervised, right? If it is just for one category, like just stats?
No, you can do it for several. There are GANs that can generate several different kinds of things. It can generate, not on command necessarily. I'm not sure if there's ones where you can say like, I only want you to generate pictures of foxes. But if it was trained on foxes, cats, and dogs, it can generate foxes, cats, and dogs, not a mixture of the two. It's not going to generate cat dogs.
And in that case also, it doesn't require a pre-labeling of cat, dogs, and dogs.
No, that's the magic behind it. Because what it'll do is it'll figure out the distribution of those features, and so you'll have like this tri-modal data. Instead of just having this one bell curve, you'll have like one little curve there, and one curve there, and one curve there. So because as it's reading through these images, it'll be like, wait, this one's a little different than all those other ones I've seen. So I'm going to start making like a local maximum over here. It's like a separate, so it's because like I said, they can do that clustering. Unsupervised networks can do that clustering of data. So it'll figure out on its own that there's 3 different types of things that you're giving it. Of course, that takes more training and more time, but.
Then the GAN will be working on 3 different distributions, right?
Yes, it'll have several, but it's really one distribution. It's just going to be a more complex distribution. Does that make sense?
How, when we click on generate, how the return will be saying that which image is going to be generated? It could be one of them, right?
Right. It'll probably just, yeah. I'm not sure myself exactly because I didn't end up making a GAN that works on multiple different classifications of data, so I haven't done a whole lot of research in that department. But I don't know if it's just randomized, like if it's literally like just go for this feature set or go for that feature set. It might just be that. If it's that simple, then great. Or it could, like you said, it could have 3 different distributions that it's keeping track of, and then it just kind of picks them at random. I think there's got to be some randomness in there.
I see in the slides you have MNIST data where we have 9 different categories.
Right.
10 different categories. How that is being trained? Is it trained? I'm just asking, right?
Yes.
10 distributions, or it's just a mix of distribution? And does it give, if you click generate, will it generate a random?
Yes, it'll generate basically a random set based, but it should match the distribution of what you gave it as input. So if you give it an equal number of 1s through 9 or 0 through 9, then it should, in theory, generate an equal number of 0s through 9s. So in that being said, I do think it's the same distribution. I think you have all 9 numbers on that same curve. But I mean, all I know is that it's able on its own to cluster each type of number. So whether it does that with 1 distribution or 10, I don't know if that's super, you know, if it really affects it a whole lot. Badri, I don't know. Can you answer that question? Do you know?
One sufficient. You have to separate out as 10 or 11 or how many ever.
Yeah.
But if you allow the discriminator to give a more refined feedback, saying 1 is a 1 and 2 is a 2, then you can actually separate out and store 10 different networks with just one network.
And it's a mix of supervised and unsupervised.
Yes, so it depends on what the discriminator is willing to give. It's just a bit saying yes, it's realistic, no, it's not realistic. Then you represent how many other modes you have on your data in just one representation.
Yeah, that makes sense because if you have 10 different distributions, then you can tell it, hey, give me a bunch of 9s. You know, but if you only have 1 distribution, then it's going to give you a random sequence of numbers and you can't necessarily tell it which one you want. Because again, it doesn't know the labels. It doesn't know which one's a 9 and which one's a 1. It's going to give you one of the pinnacles. Yeah. All right, I know I kind of went over, but there was nominations, so I excuse myself. But yeah.
All right, I know you said nominations, so I guess just to close out nominations real quick, anyone else either want to like accept or reject their nominations right now or nominate anyone else? Oh yeah. All right, that's just Which meeting. Yeah, I'll talk about it real quick. But thanks so much, Daniel, for such a great talk. Super informative and super fun. Just to go over real quick, the year is ending out, so there's not much chance for us. But if you do have something in mind, definitely keep it. Definitely bring it up so like maybe we can see it next year. Do join our sibling organizations. And speaking of sibling organizations, ACMW. Oh wait, is it Sorry, it was WIT. My bad. I typed ACMW. But WIT's meeting is happening right now, so if anyone's interested, feel free to join that. Scan that QR code. It is a talk on Imposter Syndrome in Tech by Tessa Weidman, who was actually a WIT alumni as well as Revolution UC alumni, and she works at Microsoft right now. So I bet it's going to be a super fun meeting. So if anyone's interested, feel free to scan that QR code and join it. I know I will be right after this meeting. But other than that, thank you so much for coming, hang out with us in Discord and Slack, and definitely come to our next big elections meeting. It's going to be super important, and we really appreciate you coming. And if you've come to this meeting, and if you come to the next one as well, that means you're eligible for voting and running. So you won't have to worry about that. To close out, thank you so much for coming. And if you haven't yet, fill out the form for attendance, and hope to see you in 2 weeks. Woohoo.
Take pizza.
Oh yeah, please take pizza.